One of the very last things we're going to have to take a look at regarding electric fields are the properties associated with non-uniform electric fields. Now, to understand that or to relate that to what we've spoken about previously, when we first looked at gravitation, and again, I always use gravitation because it's pretty synonymous with electricity. When we looked at gravitation, non-uniform fields would be like the fields around a planet. So we could use 9.81 for acceleration when we're on the surface of Earth, but once we travel far away from Earth, that's no longer a non-uniform. I'm sorry, that's no longer a uniform field. We can't use that number. Things change as we get further away from these planets. There were four things specifically we looked at: the gravitational force, and what happened as we got further from a planet; the gravitational field strength, right? That was the property of the planet itself. You did not need the second mass. Potential energy, again, a property of the actual spaceship that was in that location; and gravitational potential, another property of the planet, and it tells you how much energy you'd get when that other mass showed up. So these are the four things we covered fairly extensively, so they shouldn't be anything new. And if you remember these and you understand what each of them indicate, then the next concepts we discuss regarding electrical fields are going to be very, very easy to understand. So to relate what we looked at with gravitation with electricity and electrical fields, it's going to be the same thing that we looked at in like the previous video, the previous lessons. All the concepts are identical. However, instead of masses, we deal with charges. There's going to be something now because this is the universal gravitational constant, and we're not dealing with gravity anymore, so that's something else we'll have to adjust. So just to show you, if instead of having a planet and a space shuttle, we had one charge and then a second charge, the concepts are the same. If I want to calculate what we call the electric force, it's going to be KQQ over R squared. You'll notice that it's very similar to GMM over R squared. However, the only differences are that the Q's, which are charge, are now being used instead of mass. So instead of using mass in terms of kilograms, we're using charges in terms of coulombs. One is a large Q, one is a small Q here. There's really no difference. You could call them Q1, Q2. I just like to keep in line with what we've done before. So the big M was the mass of our planet, little m was like the mass of the space shuttle. Here it's just Q is generally the bigger charge. I'm sorry, capital Q is the bigger charge, lowercase q is generally the smaller charge, but it doesn't matter. You could call it Q1 and Q2 if you'd like as well. Now the only difference is K. K is still a constant, just like G is a universal gravitational constant, 6.67 times 10 to the negative 11th. We use a constant, but it's going to be different. And here it's a much larger constant, and Coulomb's constant is 8.99 times 10 to the ninth power. So it's a much larger constant. But if you take a look and you realize that these are the same setups in terms of these gravitational equations, but I use a different constant and I replace the masses with charges, everything else is identical. So if I'd like to calculate the electric force, a constant times charge 1 times charge 2 divided by the distance between them squared. Very similar to up here. Electric field strength, K, that constant, times Q over R squared. Just like the gravitational field constant is Gm over R squared. We know here the potential energy is Gmm over R. So if you could think about it, you can probably guess that this will be KQQ over R. And just like the electric potential will be KQ over R, you can see that gravitational potential is Gm over R. So I apologize for kind of jumping back and forth between these as rapidly as I am, but I do want to highlight the fact that there's no difference conceptually. The only difference is we use a new constant because we're dealing with charges instead of masses, and then we just replace the variable for mass with the variable for charge. And everything else is exactly the same. So just to show you a quick example, I'm not going to go too deep into this because, as I said, it's identical concepts, but just to show you how we would use these. Now let's take a look at this example. I have my first charge, which I'm going to give a value of 8 times 10 to the negative 6 coulombs. The reason I give a times 10 to the negative 6 coulombs is that 1 coulomb is actually on par with like a lightning bolt. Lightning bolts are anywhere from maybe 1 to 10 coulombs, so it's an unbelievably large amount of charge. If you're not dealing with lightning bolts or power plants, you're not going to see 1 coulomb, so it's much more common to see smaller values. So I'm going to start to become a little bit more realistic in my examples. So let's say I have one charge which has a charge of 8 times 10 to the negative 6 coulombs. There's no negative here, so we can assume it's a positive 8 times 10 to the negative 6 coulombs. And then 2 meters away, I have a second charge, which is positive 2 times 10 to the negative 6 coulombs. You'd typically be asked to find these four things. The first being the electric force, the second being the actual electrical field strength, the third did not finish this for some reason, but that would be the electric potential energy, and the last would be the electric field potential, which we usually call voltage. That's why we represent that with a V. And that'll make more sense as we start to get into things like circuits and batteries and things along those lines. But really quickly, just to kind of show you how we use these, exactly identical to our gravitational calculations. If I want to calculate the electric force, it's KQQ over R squared. So my constant is 8.99 times 10 to the ninth. Charge 1 is 8 times 10 to the negative 6th. Charge 2 is 2 times 10 to the negative 6th. And the distance between them is 2 meters, and I'll square that. When I calculate that, I get 0.036 newtons. Now, in order for direction, this is where it becomes tricky because this is kind of at an angle. It's not necessarily going left or right, up, down. So we generally define these as either repulsive or attractive forces. Since these are both positive, we know they'll be repulsive, and therefore my final answer would be about 0.04 newtons repulsive. So it's a repulsive force. Wherever I place this thing, if it's 2 meters from that, it will experience that repulsive force. Similarly, if I'd like to know the field strength, well, the field strength is a property of this larger charge, so I don't need that other charge. It tells me how many newtons of force per coulomb I'm going to be getting. So KQ over R squared. Here's Coulomb's constant, the charge in question, the distance from that charge, and I get about 17,980 newtons per coulomb. Now that seems very high, and again, the reason for that is because a coulomb is a very large unit of charge. So you'd expect to get this many newtons of force if 1 coulomb of charge actually showed up. That would be like if a lightning bolt ripped right through the space around this charge. That's why this value is very high. And again, it needs a direction, so we're going to say away from the charge because it's a positive charge. And if I bring another positive charge near this, I'm going to get a large amount of force, and it's going to be repulsive. It's going to point away from the charge. Electric potential energy, same thing. Coulomb's constant. Charge 1, charge 2. In this case, the distance is not squared. And that tells me that this little charge here has roughly 0.072 joules of electric potential energy. And last but not least, that electric field potential, that voltage. It's going to be KQ over R. So again, I left out the exponent here, but it's 8.99 times 10, there should be a 9 here to the ninth, times the charge in question divided by the distance, and I wind up finding that if I'm 2 meters away from this charge, well, for every coulomb that's placed at that location, I will get 35,960 joules per coulomb. Again, why is that value so large? It's because a coulomb is an extremely large amount of force. So yes, I would expect to have this much energy if I placed a coulomb at that location. That would be like throwing a lightning bolt at that location. You know just from experience that lightning bolts carry a large amount of electrical energy. That's why they can do so much damage. And that's why when we deal with things in terms of coulombs, we get very large numbers. So again, just to reiterate, I hope I didn't go through that example too quickly, but the biggest takeaway should be that if you understand these gravitational concepts very well, which we spend a lot of time on, the only difference with electrical charge is that we deal with Coulomb's constant and we deal with charges instead of masses. Every other conceptual question, every other mathematical solution will be based on the same exact principles. So that needs to be the biggest takeaway you take from this lesson.